Welcome to this Masterclass Explainer. If you're prepping for a big physics exam or, if you just want to decode the hidden rhythms of the universe, you are exactly where you need to be. Whether we're talking about the shock absorbers on your car, the strings of an acoustic guitar, or the steady swing of a grandfather clock, today we are going to make this physical phenomenon completely visual, intuitive, and unforgettable. We are going to build your absolute ultimate study guide for simple harmonic motion.
Here is exactly what we're covering today. 1. Defining simple harmonic motion. 2. The anatomy of equations. 3. The engine and the currency. 4. Springs versus pendulums. And finally, 5. The final blueprint summary.
All right, let's kick things off with Section 1, Defining Simple Harmonic Motion.
Okay, let's dive right into this matrix. What actually separates chaotic motion from perfect, predictable oscillation? Well, on the left, we have simple rectilinear or projectile motion, kind of like throwing a baseball. It happens once, and it doesn't repeat. In the middle, we've got periodic motion, like a planet in orbit. It repeats over time, sure, but look closely at our checklist. It entirely lacks a true equilibrium point and a restoring force. And that brings us to our target on the right, oscillatory motion. It repeats, it has a central equilibrium point, and it relies heavily on a restoring force. Test yourself real quick. Where would a bouncing basketball fit in? Well, it repeats, but without a central equilibrium point driving it back through a center line, it's just periodic. It's not a true oscillation.
Listen, if you take only one single concept away from this first section, let it be this exact quote. The defining signature of an oscillator is the equilibrium point. This 0 point is absolutely crucial. It's the anchor of the entire system. It's the ultimate destination that the object is constantly trying to reach. But because of its own momentum, it constantly overshoots, forcing the system to pull itself back from the extremes over and over. It's literally an eternal game of physical tug-of-war.
Let's move on to Section 2, the anatomy of equations.
We're looking at the secret architecture of the math here, the hidden language governing the movement. Picture a peg standing up on a rotating disc, like a record player. Now imagine shining a bright spotlight on that disc so it casts a shadow onto a wall. As the peg moves in a perfect, uniform circle, its shadow moves strictly back and forth in a straight line. And this brilliantly illustrates why we use the geometry of circles, specifically the sine and cosine wave functions, to map linear back and forth motion. That one-dimensional shadow of circular motion, that is simple harmonic motion. The circle is the secret, hidden architecture of the wave.
So, let's look at the governing equation itself. X of t equals a times cosine of omega t plus phi. I know it looks like a lot, but let me be your guide through this dense formula, because once you understand the individual parts, the whole thing just clicks. X of t is simply your output. It's where the object is at any given second. A is the amplitude. Think of this as your absolute physical limit, like the maximum stretch of a spring or the absolute highest point of a swing. Now, the phase constant, phi, often trips students up, but honestly, it's just the starting line of our stopwatch. A super helps mnemonic for your exams. Think of phi as the first position. It's exactly where the object was sitting when the clock struck 0.
Now, tucked right inside that cosine function is perhaps the most important variable of the whole shebang, omega, or the angular frequency. I like to call this the speed of time for the system. Why? Because it completely dictates the rhythm. A high angular frequency means our spring is vibrating furiously. A really low angular frequency means it's a slow, lazy, sweeping pendulum. Mathematically, it is defined very simply as 2 pi divided by the period t.
Now, what's really interesting about this slide is how the displacement, velocity, and acceleration curves are all staggered against each other. If you're ever asked to draw these on an exam, here is the secret trick. Always, always align the peaks of the velocity wave vertically with the zero crossings of the displacement wave. This isn't just a random coincidence. Velocity is the mathematical derivative of displacement, and acceleration is the derivative of velocity. What you are looking at right here is calculus translated perfectly into real physical space.
Let's crystallize this visual data into a rock-solid rule so you can avoid a massive, super common exam error. Memorize this phrase right now. Maximum stretch equals 0 speed. Makes sense, right? And its absolute highest displacement, the object has to momentarily stop entirely just to reverse its direction. But acceleration is perfectly out of phase with displacement, so that exact same split second of maximum stretch where speed is 0, your acceleration is violently peaking, yanking the mass back toward the center.
Which brings us nicely to Section 3, the engine and the currency.
We're shifting focus from how it moves to why it moves. The engine of this entire system is Hooke's law, the restoring force F equals negative kx. Let's really focus on that negative sign for a second. It's not just some mathematical quirk, it is literally the entire reason oscillation exists in the first place. I describe this force as being intrinsically rebellious. It always violently opposes whichever direction the mass tries to escape toward. The further it strays from equilibrium, the harder the system pulls it back. Think of a heavy jumper on a bungee cord. The further they fall down, the more violently that cord wants to snap them back up.
Let's step through how this physical movement builds into a complete energy model. If we break down the 3 phases of a swing, it perfectly demonstrates this flow. Step 1. At the extreme outer edge of the swing, the object is momentarily paused, right? So it holds 100% potential energy. Step 2. As it hurtles back towards the center, that energy is trading hands. Let's call it 50% potential and 50% kinetic. And step 3. As it flashes past the absolute center, the mean position, the spring is totally relaxed, meaning 0 potential energy, but the mass is moving at its absolute maximum speed. Bam! 100% kinetic energy. Honestly, the best way to think of this energy metabolism is like a giant teeter-totter. Energy essentially acts as the currency of the system. In a perfect simple harmonic oscillator, you're just constantly converting currency back and forth between the kinetic bank and the potential bank. The teeter-totter tips smoothly, perfectly synchronized with the physical movement of the pendulum, never losing a single cent. Notice that straight, perfectly flat line running across the top of the energy graph? That represents total energy, and it proves that the total mechanical energy is completely independent of time. It's a locked system. The initial pull, your amplitude, determines the total energy budget for the whole ride, and from that moment on, it is a flawless, zero-sum game of internal exchange.
Moving on to Section 4, Springs versus Pendulums.
Consider this your ultimate cheat sheet. This is the matrix of symmetry between linear systems, like springs, and angular systems, like pendulums. Just look at how nature uses the exact same mathematical blueprint for completely different physical objects. Mass in a linear spring perfectly translates to the moment of inertia in a swinging pendulum. Linear force translates perfectly to rotational torque. Even the period equation is a mirror image. For a spring, it's 2 pi times the square root of mass over the spring constant k. For a pendulum, it's 2 pi times the square root of length over gravity. If you memorize this symmetry, you effectively cut your studying time in half, for sure.
Okay, so I have a bit of a trick question for you. Is the simple pendulum, arguably one of physics' most famous examples, actually a true harmonic oscillator? Or is it an imposter? Think back to our strict definition of the restoring force from earlier. We said it has to be purely proportional to displacement.
Well, the shocking truth is, it's an imposter. Actually, scratch that. It's an imposter until we use a little trick. You see, the restoring force of a pendulum actually relies on the sine of theta, which is a curve, not a straight linear line. However, nature offers us a pretty brilliant loophole. As long as the swing is kept really tight, specifically under 20 degrees, the value of sine theta is virtually identical to theta itself when measured in radians. The math magically linearizes. So as long as you use small angles, the imposter becomes the real deal, unlocking perfect simple harmonic motion. This is known as the small angle hack, and you will definitely need to state this assumption constantly in your physics exams.
Let's synthesize all of this into one master model in Section 5, the final blueprint summary.
This dashboard perfectly unifies the what of motion, the why of force, and the currency of energy into one master model. So the crucial point is right here at equilibrium. At the exact center, where x equals 0, the restoring force completely abandons the object. The spring isn't pushing or pulling at all. But because it has built up pure kinetic inertia, that inertia drives it blindly right past the center line, immediately planting the mathematical seeds for the exact next cycle to begin. It's just a gorgeous, self-sustaining loop. And finally, here is your foundational blueprint. If you only memorize 3 absolute pillars from this entire explainer, let it be these. Pillar 1, the definition equation, x of t, mathematically mapping the exact shadow of the circle. Pillar 2, the engine, F equals negative kx, that intrinsically rebellious force constantly demanding a return to center. And Pillar 3, the currency, total energy equals 1/2 k times amplitude squared, mathematically proving the universe keeps a strict zero-sum ledger of potential and kinetic motion.
Now, in a perfect, frictionless theoretical universe, this blueprint guarantees eternal, unending motion. It would literally oscillate forever. But, as we know, we live in the real world. So I want to leave you with this final provocative thought. What actually happens when friction enters the equation, acting as a dampener, slowly bleeding the energy away and turning this flawless geometry into total silence? Well, that transition from simple to damped oscillation is an entirely new mathematical adventure, and it's one I highly encourage you to explore next. Thank you so much for learning with me today, and best of luck with your exams. You're going to crush it.